So let's talk about one-dimensional kinematics some more. Now, we already looked at our equation for average velocity, right? That your average or your constant velocity is equal to change in position over a change in time, or the displacement over time. But keep in mind that this equation can only be used if you are dealing with an object that has a constant speed, or if you're just looking for the average speed. Now, if we've got acceleration, right, which is defined as your change in velocity over time, you have to derive 3 new kinematic equations to use. All right, and so those equations that we come up with are the following. Now, notice the notation here. If you see that little 0 as a subscript, that's just called naught. So that would be V naught right here, and that just means initial. Right? Naught is just British talk for 0. So we got V equals V naught plus AT, which means that the final speed is equal to the initial speed plus acceleration times time. Our second equation says that your final speed squared equals your initial speed squared plus 2 times acceleration times displacement. And your last equation tells us the displacement is equal to your initial velocity times the time plus 1/2 of your acceleration times time squared. Now keep in mind that bottom equation, time is the only thing that is squared there. Alright? So what does this look like in terms of problem solving? Now, in physics, we always want to show your work. Alright? Because when you're looking at AP exams, the actual correct answer is only worth 1 point. Right? The remainder of those points come from showing all of your work. So let's get used to being as thorough as possible in our work. So what I want you guys to do, right, at least in these early stages, is use what we call the guess method. Meaning first, just list your givens. Second, list your unknowns. Third, write down the equation you plan to use. Now this equation does not have any of these plugged in, right? Do not plug your givens in. Just show me the bare naked equation, right? So something like V equals V naught plus AT. Right? So your equation with nothing plugged in. Because I can guarantee you in every single AP problem, there is a point dedicated to just showing the equation with no numbers. Alright, finally, substitute, and then solve. Right, make sure that your solution has a unit in the answer. Right, if there's no unit of measurement in your answer, you don't have a correct answer, because the unit of measurement is very important. So givens, unknowns, equations, substitute, solve. Now in more complex problems, it also helps to draw a picture and list your givens and unknowns on the picture itself. So let's kind of model that together. So in this example, we've got a car that has an initial velocity of 15 meters per second and undergoes a constant acceleration of 3 meters per second squared. What is the final velocity of the car after 9 seconds? Alright, so let me list my givens here. We know that there's an initial velocity, so V naught is 15 meters per second. Acceleration is 3 meters per second squared. Your time is 9 seconds, and we want our final velocity. So switching back to the board cam, right? These would be our givens and our unknowns. Right? We're given that your initial velocity is 15 meters per second, right? V naught is initial. Your acceleration is 3 meters per second squared. Time is 9 seconds, and we want to know the final velocity. So we've gone through the first 2 steps of guess. Next, we just want to look at our 3 equations. Which one do we have enough information to solve with? Well, we can solve this using V equals V naught plus AT. And again, never plug in any of this into your equation until you've shown me the naked equation. Alright? So now we know what equation we're going to be using. Let's go ahead and substitute in our values. Final speed is still unknown. Initial speed is 15 meters per second, acceleration is 3 meters per second squared, and time is 9 seconds. So solve that out, and we get a calculator here. 3 times 9 is 27. You get a speed of 42 meters per second. So again, givens and unknowns, equation, substitution, solution. So as you go through and practice these problems that I'm posting on Google Classroom, make sure that you are showing this work every single time. Right? You see how much work I show, you better be showing at least that same amount. Alright, now let's take a look at a very specific instance of one-dimensional motion. Now when you're talking about the horizontal motion, there's really not much conceptually there, right? It's just about identifying velocity, acceleration, time, right? It's about acknowledging that if you've got a velocity vector and an acceleration vector that point the same direction, the object speeds up. If your velocity vector and acceleration vector point in opposite directions, the object's slowing down. Now, most of the concept comes in the state of free fall. And basically what free fall tells us is that anything that is in a state of free fall will fall at the same rate regardless of mass. Right? By definition, anything in free fall is under only one force, the force of gravity. Therefore, it only has one acceleration, the acceleration due to gravity. Right? So any object in free fall is under the effect of the same gravitational force, meaning that, or actually not the same gravitational force, but the same gravitational acceleration, meaning that they will fall at the same rate. So it doesn't matter if you take an elephant and a tennis ball and throw them off the roof, they're going to fall at the same rate of 9.8 meters per second squared. Now, free fall scenarios are a bit of a simplification, but they work if we take into account 3 factors. It will work if the object's relatively heavy compared to its size, if it falls for a relatively short amount of time, and if it's moving relatively slowly, meaning it doesn't hit terminal velocity. So if those 3 conditions are met, we can treat the object as if it's in free fall, meaning that the air resistance is negligible. And what I would do is I would recommend going on YouTube and Googling, feather versus bowling ball in a vacuum chamber. And you can see that when they empty out the air from this giant vacuum silo, this feather and this bowling ball fall at the exact same rate because there's no air resistance. They're both in a state of free fall. So I Google that, or I YouTube that. Now, again, your acceleration due to gravity on Earth is 9.8 meters per second squared, and we have a special variable for that. It's just lowercase g. Now, one thing to be careful of. Little g is not gravity. If you say gravity, you're talking about the force. Little g is the acceleration due to gravity. So you want to be clear when you're explaining things conceptually, right? If you start talking about all objects falling at g, which is gravity, you're going to be marked wrong because g is not gravity. G is the acceleration due to gravity, right? It's the acceleration caused by the force of gravity. Now, if we look at different planets in the solar system, obviously the rate of acceleration varies based off of the mass and the radius of the planet, which we'll get into when we start talking about gravitation. But just look at the varying factors. The sun would have a gravitational acceleration value of 275 meters per second squared, assuming there was a solid surface to stand on. You go all the way down to Pluto, right? Pluto has a gravitational acceleration of 0.7 meters per second squared. So very, very small. But again, this is the big thing here. Any 2 objects, regardless of mass, will fall at the same rate. So go find YouTube videos so that you can see that actually happen, because that's the common misconception. Because we're so used to having air resistance present that your brain wants to say that heavier things fall faster, right? So that's a misconception you want to clear up. And actually, you know what? I'll find that video and post it here along with the notes as well.
Please release your freshmen and takeout students.
All right, so let's take a look at an example here of
takeout students.
Free fall. So we've got John. He drops a rock down a 12-foot well. How long will it take to reach the bottom of the well? All right, so y You know what, let's just change that feet to meters just to make our lives easier so we don't have to do any conversions right now because we're going to keep getting interrupted by the intercom. So y is 12 meters. Well, why am I using y instead of x for displacement? Just because it's a vertical problem. So you can always switch your variables for displacement between x and y. Y is typically your vertical displacement. X is going to be your horizontal displacement. All right, so your displacement is 12 meters. And we want to know how long it takes for that rock to hit the ground. Well, it looks like we don't have enough information, right? Well, there's a couple things that you can deduce from this problem. Well, we know that the acceleration is 9.8 meters per second squared. And we know that the initial velocity of anything that you drop is 0. Now, this problem has all of these things going down, correct? So what should we be doing here to our values? Right? If we want to have a direction scale, right, down is going to be negative, up is going to be positive. Your displacement is a downward displacement, so negative 12. And your acceleration due to gravity is a downward acceleration, so negative 9.8 meters per second squared.
Please release your sophomore students.
So,
please release your...
We have enough information to solve now using that third kinematic equation, where y equals v naught t plus 1/2 acceleration times time squared. Notice I switched out a with g because g is the same thing as acceleration in this case. So negative 12 meters is equal to 0 plus 1/2 of negative 9.8 times time squared. All right, so go ahead, solve out, and what do we get? 12 divided by 4.9. And you get 2.45 seconds. Box your answer. And again, make sure you've got units in your final answer, otherwise it's an incorrect answer. Alright, so I'm going to post a couple of problem sets up as well. One that will deal with horizontal problems, one that will deal with vertical problems. And let me know during the live engagement if you have any questions at all. It's kind of hard to do free fall like this just because usually I've got a lot of demos going on as well. But yeah, I will see you guys soon.